In this video, we want to derive the result of the period of a simple pendulum. All right. So a simple pendulum is, of course, just a mass that is hanging by a string and it's free to swing. And the simple pendulum is the case where the mass is much more massive than the string that's holding it. We usually take the string or the rope or whatever to be massless. That's of course not physically the case, but in most cases, especially in the laboratory, you may have just a few grams of string and you may have a couple of hundred grams or more of mass hanging off of it. So the mass is always going to be, for our purposes, much more massive than the string. And the second condition is that the angle that we pull the pendulum back initially is a very small angle. Okay, so usually less than 20 degrees or so. Now, here we have a diagram of the pendulum. So the dotted line represents the vertical that the pendulum would, if it were not swinging, it would just rest here. Okay, this is called the equilibrium position for the simple pendulum. And so I'm going to pull it back a little bit along this arc, and I'm going to release it from this point. And of course, it's going to just swing back and forth then, all right? And that's what the motion of the pendulum is. It just swings back and forth. But that kind of mimics the mass on a spring, right? It just bounces up and down, whereas the pendulum just swings back and forth. So we may assume that there's some sort of mathematical similarity between the two systems, and it turns out there is. So the point here is to derive a Hooke's law, quote-unquote, equation for the simple pendulum. And there's a few different ways you can do this, but we're going to do this without invoking torques, okay? Now, again, this is just the simple pendulum. This is different than the physical pendulum. And the physical pendulum is the case where your object connecting the pivot point to the pendulum bob has some mass to it. It may be like a rod or a stick or something of that nature, and in that case we actually have to take the moment of inertia of that object into account. But in the case of a massless string, then the derivation I'm about to do is a perfect, it's perfectly applicable. Okay? So if I look at my pendulum bob as I've pulled it back to this starting point here, I can see that I have my weight, and my weight is acting straight down, as it should, straight toward the center of the earth, but the tension in the string is acting up at this angle. Okay, now I've pulled it back an angle theta, and if you look at the free body diagram of the inclined plane problem, you may remember that we have gravity straight down, but the normal force coming off at some angle. And that's very similar to the situation we have here, so we invoke some of the inclined plane type of mathematics. And doing so, we note that there should be a component of my weight that's canceling out tension, just as there was a component of my weight that canceled out the normal force along the inclined plane, and that means there's a component that is causing the acceleration. So this mg cosine theta, this is my right triangle right here, and this should be a right angle, making my weight the hypotenuse. And since this is the component that is canceling out tension, it is the adjacent side to the angle, so this component is going to be my hypotenuse times the cosine of my angle, or mg cosine theta, and the component that's actually accelerating it is going to be mg sine theta. Now notice, okay, this component is in the instantaneous direction of motion, okay? So I'm going to be swinging along this arc, and this mg sine theta is instantaneously tangent to my curve and in the direction of my motion, okay? So mg sine theta happens to be the net force acting on my object. So I can set ma equal to mg sine theta, all right? Now, to get this in a form that looks something like Hooke's law, remember what Hooke's law says. Hooke's law says that if I can get the second derivative of a coordinate proportional to that coordinate as a function of time, then that is my Hooke's law form, and the constant of proportionality will be the square of my angular frequency. All right? So here's how we do this. Now in the case of the inclined plane, remember that the plane was constant, so the angle was constant. Well, here theta is constantly changing. As I'm swinging, this angle is constantly going to be changing. But if I look at a section of the path, we'll call this the section of path that I look at, I'll call that delta S, all right? That's an arc length. And if you look at the total path that the pendulum can make, it's going to be a circle, okay? And so the arc length is a small patch along the circle that is a distance along the circumference that you can move. And there's a relationship between the length of an arc length, the radius of curvature, in this case, the length of my pendulum L, okay, and the angle. And the relationship happens to be delta S is equal to L delta theta, okay? And this comes from the relationship S equals R theta, or theta equals S over R. Right, and that's a simple result from geometry. An arc length is equal to the angle in radians that the arc length subtends multiplied by the radius. Okay, so this definition holds. Now, if I differentiate this, well, actually, let me write it like this: S equals L theta. And what I want to do is differentiate this with respect to time. And technically I would have to use the product rule and then take theta dl dt, but the length of my pendulum is constant, so that term would go to 0. So if I just look at differentiating an instantaneous, infinitesimally small portion of time as the pendulum moves along this arc, okay, then the change in the arc length per unit time is going to equal the length of the pendulum times the change in the angle per unit time. And d theta dt is nothing but omega. Now, if we consider small enough time intervals, then ds is essentially going to be a straight line. Okay? If I look at a curve and I blow it up, the curve turns into a flat line. And so, if I look at infinitesimally small time intervals, ds dt is the instantaneous velocity of the pendulum along the curve. So this becomes v equals L omega. Okay? V equals L omega. And we have acceleration here, so I actually want to differentiate this again. So if I differentiate it again, I'm going to get dv dt is equal to L times d omega dt, and that is equal to the angular acceleration. Okay? So dv dt equals L alpha. So what I can do, since this equals A, okay, what I can do, since this equals A, I can plug this in into this equation, and I'll get ml alpha is equal to mg sine of theta. All right? Now, there's one more thing that we have to do before we go any further, and that is to recognize that because the pendulum is always going to be swinging toward its equilibrium position, that means we have to insert the negative sign in here. Okay? So, what that essentially means is as the pendulum moves toward the equilibrium position, once it gets here, it's going to have too much kinetic energy to stop, so it's going to keep moving, but it's going to start slowing down. And that means it must be experiencing an acceleration, and if its acceleration is opposite its direction of motion, and it's moving this way, then the acceleration must always be pointing toward the equilibrium position. And that holds throughout the entire path. Okay? And again, that's what the negative sign indicates. So we insert our negative sign in both equations, and if the string is massless, then the only mass that we have to worry about is the pendulum bob, so those m's must be the same, they can go away, and we have L alpha is equal to negative g sine theta. Okay? Now, as I said before, one of the conditions of the simple pendulum is that the angle is small. So when I pull it back, it's less than 20 degrees or so. If that's the case, we use what's called the small angle approximation, and it says that for small theta, sine theta is essentially equal to theta. Now, you have to do this in radians, but if you punch into your calculator, sine of theta for a really, really small angle in radians, like 0.001 radians, and you take the sine of that, you should get something really, really close to 0.001. So the sine of 0.001 radians is really close to 0.001 radians. So for small angles, this holds. So we replace the sine theta with just theta itself and divide both sides by L. And now we have arrived at the result we want. And this is a form of Hooke's law for the simple pendulum. I have an acceleration, rotational acceleration is proportional to a rotational coordinate, and the angle. And we have our negative sign and my proportionality constant. So what that means is that the angular frequency of the simple pendulum is given by G over L. The square of the angular frequency is given by G over L. Okay? The square of my angular frequency is given by G over L. And that means that the period of the pendulum, if you recall, the period is equal to 2 pi over omega. And so omega equals the square root of G over L. So 2 pi over the square root of G over L is 2 pi times the square root of L over G. So that is one way that you can derive the period of a simple pendulum. Your book does it with torques, and I invite you to read that, but it's also instructive to understand this method too, and then to see that the two are in fact equivalent. All right. So that is how you can derive the simple pendulum of the or the period of the simple pendulum, and we'll see you next time.